Greetings. What we're going to look at today are the solutions for non-homogeneous differential equations. Now, the last video, we looked at homogeneous differential equations, equations like this. Now, you notice the difference here. Here's a non-homogeneous differential equation. See, it's equal to something non-zero over here, and here's a homogeneous differential equation. So here's the general form of here for non-homogeneous. Okay, it's equal to g of x. When we replace the g of x with a 0, we get the non-homogeneous differential equation. Now, so I want to make a connection with when we talk about the solutions for the non-homogeneous to what we've found about the homogeneous. Recall that if we have a differential equation like this, a homogeneous, y double prime minus 4y equals 0, and we're told that these functions are solutions. So, for example, we're given e to the 2x, e to the negative 2x. We're just given a couple of functions and told these are solutions to that differential equation. We can send them into the Wronskian to test to see if these form a fundamental set of solutions. And the Wronskian, it's just the determinant. We just put it in here, and if we get something that's not equal to 0, we say, yes, those solutions form a fundamental set of solutions. And what we do with these is we can say, okay, here's the general solution for that differential equation. We've got a constant times the first solution plus a constant times the second solution. And we say, okay, this is the general solution. Okay, now, that's the homogeneous case. Let's take this same equation and change it into something that's non-homogeneous. Like, we'll replace the 0 with a 5 cosine x on the other side. Now, when I do that, I've got a non-homogeneous equation. And let's suppose that we have this solution over here. This y sub p1 is equal to negative cosine x. And I'll tell you, that's a solution for that non-homogeneous equation. We refer to that as a particular solution. Okay, so that is a particular solution. Now, let's just explore this a little bit. What I'm going to do is take the derivative. And you notice I get sine x. Okay, the first derivative of that negative cosine is sine x. And then we got the second derivative, which is cosine x. So if I put that back in this function, I've got cosine x minus 4 times negative cosine x. And that does indeed equal 5 cosine x. So, yeah, that's a solution. Okay. Now, something I want to show you. We also know that for the homogeneous case, we've got a solution up here. Okay. So, here's what I want to bring out. First thing, I want to show you that we can talk about the general solution this way. We can say, okay, e to the 2x, or c1 e to the 2x minus c2 e to the negative 2x minus cosine x. And this right here is the general solution. And what we say is this solution to the homogeneous part, that right there is the complementary function. Yeah, that's the complementary function. But notice what we've got this general solution is the complementary function plus the particular function, or the particular solution. Okay, and that forms the general solution. Now I want to just look and see, well, why would that be the case? Well, let's just look at this. Let's see if we can convince ourselves that this is true. Let's take this differential equation, and I'm going to put in the c1e to the 2x plus c2e to the negative 2x minus cosine x, okay? And I'm just changing to differential notation there. And then we've got minus 4 c1e to the 2x plus c2e to the negative 2x minus cosine x, minus cosine x. Actually, minus cosine x. And I'm saying that that equals 5 cosine x. Okay? That's what I'm saying. So I'm claiming that when I put even the solution to the non-homogeneous part in, if I put that in together with a particular solution, it's still a solution for the overall. So let's see how this works. Now, you can look at this and look what you've got here. You've got, let me just split this up. Because of the property of derivatives, I can differentiate across the plus and minus. See, I'm just rewriting this. Okay, now notice this is the homogeneous part. The second derivative of the homogeneous solution minus 4 times the solution for the homogeneous equation. And then after that, I put in this part. So I say, okay, plus negative cosine x minus 4 negative cosine x. Okay. Now, we know that this part up here equals 0 because, because this is the solution for the homogeneous case, okay, right here. So that means that that equals 0, and we know that this down here is going to be 5 cosine x. So you can see that it works out. Putting in the homogeneous part of the solution of the homogeneous equation together with the particular solution, it works, right? So in other words, it forms the general solution right there. And you can see that for sure. Okay? And we just say that this first part is the complementary function, and we put it in with that particular solution. Now, this one up here, this next one right here, okay? This is a solution for that differential equation. We'll just take that as a given, okay? That's what we'll take as a given. Now, likewise, just like with the other one, we say, okay, a general solution then is going to be the complementary solution, or the complementary function here, plus the particular solution. So we've got c1e to the 2x plus c2e to the negative 2x plus e to the 5th plus 2x. Okay? Okay, so for both of these, that's the case. Okay? Now, I want to show you how we can use both of these. We've got this solution for this one and this solution for this one right here. Okay? Now, I want to show you the superposition principle for non-homogeneous differential equations. If y sub p1 is a solution of this differential equation here, and y sub p2 is a solution for this differential equation here, here's what we've got. We've got a general solution, or I should say a particular solution of that goes this way. So look, let me just write it out here. y equals negative cosine x plus x to the fifth plus 2x. Okay? So I'm saying that is a particular solution. Now notice I've combined those of this equation right here. Y double prime minus 4y equals 5 cosine x plus x to the fifth plus 2x. Okay? So notice this right here is a particular solution for this. And notice what I did. I said, I kind of put these two equations together. I said, here's the left-hand side. It equals this, 5 cosine x, plus x to the fifth plus 2x. Okay? And we say that's a particular solution. Okay? Now, you can show that in a similar way that I went through this process down here. So it's not difficult to show, and I've already gone through that 2 or 3 times. So you see the method, and you can see how this could easily be shown. But I won't take the time right now. So let's suppose that we have, let's just state it more generally. Let's suppose that we have a homogeneous differential equation here. We have these solutions. And the Wronskian is not 0. So these form a fundamental set of solutions. And we say the general solution is this right here for that homogeneous differential equation. Okay? Let's suppose this is something that we know. Now let's suppose that we have the non-homogeneous part. Okay? And I've got a particular solution here. Then the general solution is given by this. I take the homogeneous solutions and add this to the particular. And we say that the homogeneous part here is the complementary function. Now, let's suppose, so let's go to the next thing. So this is what we know, okay? So if we have solutions to homogeneous and then a particular solution, we can form a general solution this way. Just add them. Now let's suppose I've got a non-homogeneous equation here with this as a particular solution. I've got another one here, notice G sub 2, with this particular solution. And you can have any number of these. Then we would say this, that the y sub p, a particular solution, is the sum of these, okay, for this differential equation, where we have G1 plus G2, okay? So that is the superposition principle for non-homogeneous differential equations.